All right, welcome to another IAEI News Live. My name is Thomas Dimitrovich, and today we're going to talk about, I want to start a series on grounding and bonding. They may be back-to-back, they may not be back-to-back, but I want to explore with you a great resource that the industry has, which is the grounding and bonding books and materials from the IAEI, specifically the Soars grounding and bonding resource. So let's talk Soars, grounding and bonding, and it all starts now. Hey, welcome back. First of all, I do want to say this is a recorded session. I am recording this session because I'm traveling. I actually took little Maggie, my Labrador, youngest. They're both twins. They're both the same litter. The smaller of the two. She tore her ACL. So we're headed to Columbus, Ohio, to Ohio State, to see a doctor who is going to perform surgery, hopefully soon, on her little ACL. So, in any case, I had to record this session. But I was talking to our friends down at in Texas, Paola specifically. Laura Hildreth. And Laura and I were talking about all of the resources that are available from IAEI. There are so many. Just trying to keep track of all of those and make sure that we know what's updated, what's not updated, all that good stuff. And I asked about source grounding and bonding because grounding and bonding is such a fundamental part of a power distribution system. It is fundamental and is very critical, and it is the most debated topic that I have seen in my history in the industry. So my thought process is so in talking to Laura, she was like, well, Tom, we have the 2023 edition that was updated and it's out there. I'm like, well, geez, oh man, we got to tell the world. So that's what I'm doing. So as part of that, I want to let you know that there is a huge industry resource for us through the Soars grounding and bonding resources that we have from IAEI. I would argue that it's probably the industry resource for grounding and bonding. So I would recommend that you get a copy of it if you don't already. And I want to see more chapters and divisions doing educational materials or educational sessions on this topic. And the slide deck is huge. In fact, how many slides is it? Tom, how many slides is the resource? So I am going to come up here and go to IAEI, and I go to presentations. Soars 2023 there's 3 different parts. So part 1 has 315 slide-arunos. That's part 1. Part 2 has 587 slides. And part 3 has 549 slides. So here's my message. That if you are a chapter or a division, or you are an educational person, a person who spreads knowledge, you could be with a manufacturer, you could be with a consulting engineering firm, architectural engineering firm, you could be with an electrical contractor, maybe you're an individual that your company looks at, or people outside of your company look at for educational knowledge. This resource is hours of fun. And what I've done is I just sort of went in, I'm just doing a 1-hour session as an introduction to grounding and bonding. We're going to dig into things like separately derived systems, services, sizing of the equipment grounding conductor, sizing of the grounded conductor, some fundamental rules around the grounded and grounding conductors, all that jazz. What is a grounded and what is a grounding conductor? These are all topics. And honestly, you could take this slide deck and get many 1 hour or 2 hour programs out of it to help reinforce the fundamentals on grounding and bonding. Again, a very important topic we need to understand. So what I am going to do today is I want to basically introduce you to this thing, this resource, this huge, I think, like I said, if I talk to people in the industry, electricians, engineers, and I ask them about grounding and bonding and where they get their knowledge, and they'll tell you, oh, Soars grounding and bonding book. And I'll bet you they don't even associate the Soars grounding and bonding book with the IAEI, but it's a fact that it is. So now we have the 2023. What I like about the Soars grounding and bonding book is it goes through, it helps you, it gives you some depth. It just doesn't just look at Article 250 and say, here's the grounding and bonding requirements for a power system, and it gives you the whys, it gives you depth of knowledge. And with a good depth of knowledge, especially as an instructor, you can pick and choose slides out of this entire huge slide deck. It's got to be over 1,000 slides. I mean, two something, and one was 5. There's got to be over 1,000 slides. It's a great opportunity to pick and choose some slides, talk about the topic. All right? So, now, another thing you may or may not know is that Soars is a person's name. Eustace Soars gave this content, he was the original author of the grounding and bonding book, and he sold that and sold the rights to that book to the IAEI for $1. And with the understanding that the IAEI was going to continue the development of that resource for the industry, and it has, and the IAEI has delivered on that tenfold, because it went from a small book to something that is an unbelievably great resource for the industry. It's a 8.5 by 11, about an inch thick. It's a great resource. We are on the 15th edition. The 2023 edition of this book is the 15th edition. And think about it, we update it every 3 years. That's a lot of great knowledge and information over the years. I personally have multiple editions of this on my bookshelf because I reference and I look at different editions, just because in some cases there was a little bit more, maybe a little bit less, and there were some changes in Article 250 and other sections and articles within the code around grounding and bonding. If I went back to Eustace Soars' time, he didn't have photovoltaic energy storage systems and all these other things, and technology wasn't where it was. Technology isn't where it is today. He did not have that. I don't want to say complexity, because grounding and bonding is a pretty fundamental thing. But when you pile on top all of this new technology, variable frequency drives, and all this great stuff that is helping us so much in utilization of electricity, having multiple editions on my shelf has really helped me. So the first thing I want to talk about is this thing called grounding and bonding. Honestly, I think this is a topic where many people who really get into grounding and bonding will spend hours debating this topic. I've seen it. I've seen people get passionate on both sides of the table, and I'm sitting there thinking they're both saying the same thing. ultimately they're both saying the same thing. And I think the best presentation that I have seen. Put it this way: it's not the best presentation. The grounding and bonding program that made an impression on me was when I was at, I believe, the Southern Section meeting. I think it was. Or it could have been a Tennessee chapter meeting. I don't know. Brian Holland was there from NEMA. Brian did a presentation. I'm almost positive it was Brian. And I'm not sure if he was the originator, because I know I have done this in some of my classes. But I got it off of him, and I don't know where he got it off of. But I'm almost positive it was Brian Holland who did this, at least for me, that I experienced it first. Brian had the entire audience, each row. He said, I want you all to hold hands and lift your feet off the ground. Now imagine this, in a room of like 200 people. Everybody held their hands of the person next to them, and they lifted their feet off the ground. Some had an easier time of that than others. And he said, you are all bonded to each other. Each row is bonded. I'm like, okay. He goes, now I want the person on the aisle seat to put their feet on the ground. And he said, now you are all grounded through that one person. That person is grounded. All of you are bonded. And essentially, you are all grounded through the bonds. Oh my gosh. I'll tell you what. I absolutely loved that. And when he first said, I want everybody to hold your hands and lift your feet up, I was thinking, oh boy, here we go. But I'll tell you what, that left an impression on me that has stuck with me forever. And I'm still talking about it today. I don't know how many years ago that was. But it sends an important message that I think helps us understand what we're saying here. The act of grounding something is different than the act of bonding something. And you'll see the industry argue this. Do you call it grounding? Do you call it bonding? And I have been in the discussions where an individual will say, well, it says I need to ground that receptacle. So does that mean I have to drive a rod and I have to connect that receptacle directly to a grounding electrode because that's grounding it? And then the other person will say, well, no. You don't have to ground it. You have to bond it. And the grounding is done back at the panel board where we bond the equipment grounding conductor and the grounded conductor together, and both of those are connected to ground. And you go, oh, okay. Well, then you told me to ground this, but you meant just bond it. And so the discussion goes. And I can hear that played over and over and over. But there's an important message here. There are two separate aspects. We establish how to ground something and how to bond something. Now, what you'll see here is we will say, I got these out of, okay, so I'm going to speak to it. I put the slide here, I'm going to just talk to it. What this slide is trying to tell you, what Soars grounding and bonding does a great job of, is it helps us understand that why we use the term grounded conductor. We all fall into this trap. We all call it the neutral. But in some cases, it's not the neutral, a neutral point on the system. That image at the very far bottom and left, furthest one from me on the bottom, That's a neutral point in the power distribution system, the center of a Y grounded system. And you'll see you have the ground going straight to that center P post, and then the neutral or the grounded conductor being carried with each of the phases. Well, what about that single phase, 2-wire, 1 conductor? Is that the neutral point? It's a single phase. It's one leg of the single phase system that is not a neutral. It's a grounded conductor, but it's not a neutral. The multi-phase system, corner grounded systems, or that midpoint of one of the transformer windings, is that a neutral point for the entire system? You can't call it that. So we migrated from calling that white conductor a neutral to calling it the grounded conductor because it works in all scenarios. And if we apply consistency to a term, we will use it correctly regardless of the system that we're in. You see, there is a reason for the madness to say don't call it a neutral anymore. We went through a phase in our industry, and I remember this. I remember having the debates at the IAEI section meetings and the chapter meetings and the division meetings. I used to go to many different chapters, and we would sit there and argue about, is it a grounded conductor? Is it the neutral? And then some people would say, well, grounded, neutral, what makes the difference? Well, it does, depending upon the system, right? So you'll always be correct if you call it the grounded conductor. So there is a point in the history of grounding and bonding where they quit calling it the neutral, or at least there were a lot of people who never called it the neutral. But at least there was a point in our history where there was this drive to make it a point to say that is not a neutral, it is a grounded conductor. And that's an important thing you need to remember as we explore the National Electrical Code, because if you're not going to see the terms neutral and bonding of the neutral and things of that nature in the code, we use grounded conductor. All right? So it's a very fundamental thing you need to remember and understand, and you have to understand why. Why do we go through and take those pains to get that done that way? All right? So, sort of out of sync in my discussion, but I got the point. Got the point crossed, I think. All right, so now let's talk about, again, the relationship between grounding and bonding. Honestly, I go back to that session. Hold hands, lift your feet off the floor, you're bonded. One person puts their feet on the ground, he is grounded. And we are all grounded through that one person. Another good example, there's probably a YouTube video out there somewhere of they have a whole chain and somebody creates static electricity and touches the spark and everybody in the whole chain feels it because they're all bonded together. They're all touching. And the code talks about keeping the grounded conductor separate from the grounding, that equipment grounding conductor and bonding conductors throughout the entire system except for one location, right there at the source. Whether it's a separately derived system or a service, both of those types of applications, you're going to have the bonding done at the source of the grounded and the grounding. And you'll notice every panel board downstream and all of those little terminal blocks that we buy, and we put in equipment for the grounded conductor, they're insulated. Why? Because we have rules to keep those separate. But we want everything bonded, even if you have an ungrounded system. So think about history. Back in the day, when electricity was first put into practice, what did we leverage it for? We leveraged it for manufacturing processes, for three-phase systems, for motors and things like that. And we had mainly ungrounded systems in our power distribution. Why is that? Because they wanted the reliability. And grounding was like, oh boy, that's ungood because, ungood technical term, because that indicated a problem. You should never have anything grounded. It should always be separated from ground. Well, the problem with that was you were like a ship in the ocean. You were a ship floating on ocean, and when the sea is calm, everything is fine. But the moment things start happening in that power distribution system, you've got motors turning on and off, you've got switches, you've got all these activities going on. Now all of a sudden your voltages are going to start fluctuating and then eventually lead to insulation failure, because the temporary over voltages on insulation will break down that insulation. I look at that like dropping water, drops of water on a bar of soap. One or two, not a problem. Take that bar of soap, put it in a sink, and let little drops go land on that bar of soap. Come back the next day, not a big issue. Come back a month later, and I'd be surprised if the bar of soap was even there, or portions of it were missing because of the damage over time. Same thing in those industrial power systems. They started to experience failures of motors, and then they try to solve the problem. Well, somebody had the bright idea of saying, hey, let's ground the system. That's like a boat throwing an anchor in the ocean. And now you're secured. Now that boat's going to be stable, relatively stable. Take the anchor away and you're going to be going like this. Put the anchor on and you're probably going to be going like this. So think about it as establishing that anchor for the power system. And now the voltage fluctuations go away. I don't have those problems, but I have other problems. What are my other problems? Well, we grounded the system. We went from ungrounded to grounded. In an ungrounded system, the first fault was a gimme. We have indicators in the plants that say, hey, I got a ground fault somewhere. And then there were methods to find that ground fault. And then you fixed it, and you moved on, and you never lost production. The moment we solidly grounded the system, that first fault, it's a doozy. All right? It's a doozy. So, gotta love this stuff. So, that was a problem, but it was a better solution to the overall issue of the reliability and the concerns of overvoltages. Here's the other thing that happened. This is back in the day. We grounded the systems, and they were all 208. And we took the 208 volt systems and we moved them up to 480. And then we moved it up to 480. When we moved it up to 480, my size of my services and whatnot went up as well. So I went from an average, say, a 600 amp service to a 3,000 amp services and higher. And the challenge that presented other challenges of arc flash and whatnot, because now I went to larger overcurrent protective devices. Ground fault currents, that first ground fault current was a doozy. It started causing arc flash events and all that jazz. And then we saw changes in the code to address those issues. So both of these systems, whether it's an ungrounded system or a grounded system, both have issues and concerns. Both have their place in our electrical industry for applications. The challenge we have as design engineers, designers, and installers, etc., is to pick the right one. There are some rules on what needs to have a grounded conductor, but not all systems will have a grounded conductor. And even if you have an ungrounded system, you may have an ungrounded system and still need to do all of the bonding. So whether a system is grounded or not, you're still going to need to do all of this bonding. You may not secure a ground. You may leave it ungrounded, But regardless of whether or not you have a grounded or ungrounded system, all of these things need to be bonded. The only thing you're not going to bond in an ungrounded system is you don't have a neutral point. You don't have the grounded conductor, period. You don't have a grounded conductor, so you're not going to bond a grounded conductor when it does not exist. But for grounded systems, we bond the grounded bar, that grounded conductor, with the equipment grounding conductor at one point in the system, and we keep it separate everywhere else. This is a good diagram to help us understand bonding, and this diagram helps us understand the grounding. And everything is grounded through the bonding. I can say that fluorescent light right here, right here, that fluorescent light is effectively grounded through being bonded, just like holding all those hands and having that one person on the end put their feet on the ground. I'm grounded because I'm bonded to another person who's bonded to another person who's bonded to another person who then is grounded. That fluorescent bulb light fixture, that luminaire, that fluorescent luminaire is bonded with the panel board through that green bare copper conductor, the equipment grounding conductor. That panel board is effectively bonded through that raceway, the conduit, and to the main panel board, which is then bonded with the grounded conductor and with the grounding electrode conductor, which is connected to the grounding electrode. All of that stuff has to be bonded. And the motor that comes right off of that service panel board is grounded as well, is bonded. And it's grounded through that bonding. The big key message that I think is important for us as electrical professionals is to recognize that I have to bond and then I ground. And why do I bond? I want everything at the same potential. I want an effective current path, ground fault current path, back to the source. I want to create a low impedance path such that if a fault should occur, I facilitate. Now, there's another debate. I mean, I struggle with this one. And we'll get to it. But I want to create an effective ground fault current path back to the source, realizing the fact that current will take all paths back to the source. Just the fact that I've bonded everything and I've connected everything together and I sized my equipment grounding conductors accurately and correctly does not mean that all of my current is going to go through the equipment grounding conductor. Anything that is touching, anything that is conductive and touching, current's going to pass through it. One of those lines could be me or you or somebody. One of those lines could be a dog, could be an animal, could be a mouse, anything. Current is going to pass through it. How much current? Can't tell you. Can't guarantee that I can calculate that accurately, but I can get in the ballpark. It's going to be a lot probably. Depends upon how much current is how long the circuit is, how much impedance is in the circuit. Ground fault protection, grounding and bonding. Grounding and bonding is not there to prevent electrocution. If you come in contact with, if you create a ground fault through your body, the fact that it's grounded and bonded does not mean your life is saved. Now, hopefully, if there's a ground fault in there, and it's like the whole adage, if a tree falls in the woods, did it make a sound if nobody was there to hear it, right? If the ground fault occurs and nobody touches it, but it clears the overcurrent protective device, I have avoided a shock condition because I've removed the problem. We see this in marina applications, in Article 555, they put a tiered approach to ground fault protection. They've got 100 milliamps, they've got 30 milliamps, and they have 4 to 6 milliamps protection for those piers that are out there, and the shore power and any receptacle outlets that are there for cord and plug connected general purpose. That tiered approach and the fact that you have 100 milliamps tells you any of these ground fault currents that are greater than at least 100 milliamps out there are going to open, or 30 milliamps out to the boat, etc. I'm facilitating opening those overcurrent devices by lowering the trip point. But I could have ground faults that occur that don't trip the overcurrent protected device. Are they overcurrents? That's a whole nother discussion and debate. I mean, I tell you what, honestly, tell you the truth, I recorded this earlier this morning. And I deleted it. Because, and this is the bad thing about recording things, I thought about it afterwards. I'm thinking, man, I spent a lot of time talking about, which I'm going down that road now. I spent a lot of time this morning talking about the topic of is a ground fault current an overcurrent? And the reason I went down that road is because of what you find in 250.4. But when I get to there, I'll hit that. Let's continue our discussion for this purpose for a little bit longer, and then we'll get to talking about that overcurrent discussion in 250.4. But in any case, series and parallel paths, we know it's going to take all paths back, and what we're trying to do is create the least resistance so most of the current can go through that equipment grounding conductor. We want the overcurrent devices to operate. When we lower that impedance path, we increase the likelihood of that. Circuits operating normally with current below the overcurrent device ratings will continue to operate normally, and I would say even circuits operating abnormally through a ground fault may have very low fault. If I have a ground fault and only 6 milliamps or 8 milliamps are flowing, say it's a 200 amp circuit, and a ground fault of 50 amps is flowing, it's not going to trip the overcurrent device. Is it normal? No, it's an abnormal situation. It's a ground fault, but it may not operate the overcurrent protective device. And we know that the time current characteristic curve for an overcurrent protective device is an inverse time current curve. So the higher the fault current, the faster the clearing times. So the more current through an overcurrent device, the faster the clearing. And you've seen me talk about this with regard to arc flash. You know, the old adage of if you're going to have a fault, it better be a good one, because you want the overcurrent device to do its job and clear quickly. Now, there are a lot of images in this. I like this one here because it demonstrates that when you have a ground fault, you have a connection from that hot conductor down to the equipment enclosure, and then it shows the path not going through the normal path. A ground fault current is going to go outside of the normal path. And basically bypass the circuit. Now you're flowing over the enclosure, through raceway, possibly, if that's your equipment grounding conductor method, bare copper conductors, insulated copper conductors that are there for equipment grounding conductor. In some cases, they're required to be insulated, depending upon the application. And then they'll find their way back to the service or the source separately derived system, where it's bonded with the grounded conductor, the neutral point or the grounded point, and then hopefully facilitating the operation of the overcurrent protective device, but not necessarily. This is your normal current passing a normal current, all of the current's going to stay in the path, the intended path. And the amount of current that flows will depend upon the impedance of the system. The moment I go outside of the path, now I have my impedance diagram, my Ohm's law circuit of resistances changes. I may shorten the conductors because where my ground fault occurs, and then I have the impedance of the ground return path. During a fault, there's you're going outside of the normal path and you're flowing through the equipment grounding conductor and possibly the infrastructure itself. Now, Article 250 is separated into 9 parts. Gosh, you're going to love it. Part 1 are your general requirements. Part 2 is your system grounding. That's where we talk about the fact that you can have grounded or ungrounded systems, etc., and what systems are required to be grounded. When you get into Part 3 is your grounding electrode system. Part 4 is your enclosures. Part 5, where's Part 5? I don't see Part 5. What's Part 5? Why is not Part 5 there? I hope you all have a copy of NFPA Link. I am opening that right now on my other monitor. 250. We'll look at Article 250, and we have Part 5 is bonding. So, Part 5. Jeez, oh man. It's in red over there. Part 5 is bonding. So bonding applies to all these different locations. 6 is equipment grounding and equipment grounding conductor connections. Part 7 is your methods of equipment grounding. Part 8 is the direct current systems. Part 9 is your instruments, meters, and relays. And 10 is your medium voltage applications. So the way bonding is peppered throughout various parts within Article 250. So bonding plays a very important role in the overall system. All right. Now, I'm going to focus in on 250.4. These are basically performance criteria telling us in 250.4a, just call up the language. 250.4a is your grounded systems and B is ungrounded systems. Now, in your grounded system, this is when you're intentionally grounding the system. One portion, remember the diagram that I showed you. You're either going to have the neutral, you're going to have a corner grounded delta system, etc. You're going to have a grounded conductor. In an ungrounded system, you will not have a intentionally grounded conductor. The performance criteria for a grounded system is in one of 5 parts. You have first level subdivision A, section 1. I don't know if you'd call it list item 1s or subdivisions. 1 is your electrical system grounding. 2 is, now in electrical system grounding, it tells you that you have to connect to the earth. Oh, there's a whole nother discussion. I mean, think about it. The earth, when the earth was made, it didn't come with terminals. All right, so because it didn't come with a terminal, you have to make one, and that is your grounding electrode. And Article 250 tells you what all can be considered a grounding electrode, whether it's a UFR ground, water lines, or you're driving rods into the ground. You need a terminal for earth, because essentially the system, when you say a grounded system, you're connecting it to earth, period. So what A1 tells us, What A1 tells us is that electrical systems that are grounded shall be connected to earth in a manner that will limit the voltage imposed by lightning, line surges, or unintentional contact with higher voltage lines, and that will stabilize the voltage to earth during normal operation. Remember I told you earlier, the challenge with ungrounded systems is you're a ship in the sea, in the ocean, or the sea, doesn't matter, where there's waves, and your ground is your anchor. There's NFPA 780 for lightning protection of systems, so lightning protection, grounding becomes very critical. But just during normal operation, those voltage fluctuations, which can damage insulation, are critical. Then 2 is grounding of electrical equipment. This tells you that normal, non-current carrying conductive materials, enclosing electrical conductors or equipment, or forming part of such equipment, shall be connected to earth so as to limit the voltage to ground on these materials. Now, here's the problem with that statement. Without taking the entire topic of grounding and bonding under consideration, it would seem to imply that all electrical equipment have to be connected to a ground rod. This is the beginning of the debate and discussion of bonding and grounding, and why that presentation from Brian Holland really helped me understand the fact that I'm effectively grounding everybody through maintaining bonding and grounding at one spot. We do not want to ground everything at every single point. You don't have a receptacle that you have to drive a ground rod for. We bond it, ground it. So A2 introduces a little bit of confusion that you need to step out of the box and think about. Bonding of electrical equipment. Normally, now this is 3, normally non-current carrying conductive materials enclosing electrical conductors or equipment, normal or forming part of such equipment, shall be connected together and to the electrical supply source in a manner that establishes an effective ground fault current path. So A3 is your bonding, which we had diagrams for. That whole bare copper conductor that ties all that together, the discussion that we had here, the discussion that we had here with bonding, all of that equipment. You have a bare copper conductors, insulated copper conductors, raceway, conduit, etc., acting as equipment grounding conductors, all bond everything together. That goes back to A3, bonding of electrical equipment. And then in 4, bonding of electrically conductive materials. Normally, non-current carrying electrically conductive materials that are likely to become energized, there's a whole other discussion of what is likely to become energized, shall be connected together and to the electrical supply source in a manner that establishes an effective ground fault current path. It raises the awareness again that what our goal is to establish an effective ground fault current path. We want, if there is an energization, a fault that occurs, you're not touching it for some other reason, you have a ground fault current and it energizes the enclosure, you want the return current back to the source. And then finally, in 5 is, I think, and this is where I recorded a session this morning. I deleted it. I just got rid of it because I spent a lot of time talking about this one. An effective ground fault current path. What does it mean? I have a challenge. I'm challenged with this, and I think it's the way I think that challenges me, and I'd love to know if it challenges you. But what this section effectively says, I'm going to put it on the screen here if I can. It says, electrical equipment and wiring and other electrically conductive material likely to become energized shall be installed in a manner that creates a low impedance circuit. And this is the part that gets me. Facilitating the operation of the overcurrent device. That right here. Facilitating the operation of the overcurrent device. What does that mean? What's it mean to you? So my issue, here's my thought process. If what I'm saying is that if I calculate the ground fault current at any point in the power distribution system, the first upstream overcurrent device has to open on that ground fault current. Because of that statement right there. If that's what that means, that has far-reaching implications. For example, in a residential dwelling unit, we know that we've measured faults in the power system. We can get down as low as 50 amps at the furthest part of a branch circuit, possibly lower. That's line to neutral, but what about line to ground? Would that be different? Would it be lower yet? Would it be higher? I don't know. That would trip a 20 amp circuit breaker. That would trip a 20 amp circuit breaker. But this is not a process that we do regularly. We don't calculate ground fault currents throughout the entire power distribution system and then compare it to the overcurrent protective device. Now, we do have a section in 250.122 that says, well, if you have to increase the ungrounded conductor for any of these types of reasons, then you need to consider the size of the equipment grounding conductor or do an evaluation at least. And all the evaluation has to determine is whether or not you're going to facilitate the operation of an overcurrent device. It doesn't say the instantaneous region, short time region, long time region. You just have to open the overcurrent device. So then I may need to either shorten up the circuit or put ground fault protection of equipment. So if I have a 200 amp circuit and my ground fault current is 50 amps, I could put ground fault protection of equipment at 40 amps and say, all right, I'm going to facilitate my overcurrent device is going to trip on that 50 amp ground fault current, which is it says it shall be capable of safely carrying the maximum ground fault current likely to be imposed on it from any point on the wiring system where a ground fault occurs to the electrical supply source. So that tells me that my system has to be able to handle that ground fault current. It doesn't say for how long, because it could take minutes, right? So if I'm tripping an overcurrent device in the long time pickup range, it says, what that says, capable of safely carrying the maximum ground fault current likely to be imposed on it. It doesn't say for 0.05 milliseconds, for only 2 cycles. It has to be able to carry it, period. Now, here's the other issue I have. It says facilitate the operation of the overcurrent device. If I look at the definition of what an overcurrent device is, it protects from overcurrents. And if I look at what the definition is of an overcurrent, that's a current that is exceeding the rating of a conductor or equipment. So are all ground fault currents overcurrents? Are they? I'd love to know your thoughts on that. So there's a basic question I have. Are all ground fault currents overcurrents, or are they not? If they are, then that has an implication. So anyway, I spent a lot of time this morning talking about it. I'm not going to go that route. I'm going to move on. But I have to have an effective ground fault current path. Now, ungrounded systems, we talked a little bit about ungrounded systems. We talked a little bit about ungrounded systems. 250.4b, this is when you do not have an intentionally grounded conductor. The only intentionally grounded conductor is the equipment grounding conductor. You still have bonding. So whether or not you have a grounded or an ungrounded system, you will always have bonding. You're always going to have ground rods. Think about that. You're always going to have to bond everything together. Performance criteria for ungrounded systems are in 250.4b, grounding of electrical equipment, bonding. What does it say? So let's go to B. So non-current carrying... It says non-current carrying conductive materials, enclosing electrical conductors or equipment or forming part of such equipment shall be connected to earth in a manner that will limit the voltage imposed by lightning or unintentional contact with higher voltage lines and limit the voltage to ground on these materials. Now, how does that differ than the first one? The first one said, for grounded systems, electrical systems that are grounded shall be connected to earth in a manner that will limit the voltage imposed by lightning, line surges, or unintentional contact with higher voltage lines, and that will stabilize the voltage to earth during normal operation. I don't have that language in B. There's no stabilization of the voltage during normal operations, which is one of the problems with ungrounded systems. Now, bonding, non-current carrying conductive materials, enclosing electrical conductors or equipment, or forming parts of, etc. You have to bond them all. Bonding of electrically conductive, path for fault, electrical equipment, wiring, and other electrically conductive material likely to become energized shall be installed in a manner that creates a low impedance circuit from any point on the wiring system to the electrical supply source to facilitate the operation of overcurrent devices should a second ground fault from a different phase occur on the wiring system. That recognizes the fact that the first ground fault in an ungrounded system is a gimme. You've effectively grounded your system. It's the second fault that presents the challenge. All right. I got to get back to my system. For some reason, I lost my mouse. Well, that's not good. I lost my mouse. Well, anyway. Okay, so. And you need an effective path for your ground fault currents. All right. Let me just do this. And there we go. Now I'm back. All right, so. Electrical systems are designed for the capacity of the load. We have insulation. Remember, everything downstream, you have to keep the grounded conductor separate from the grounding conductor. Those two have to be completely separated. And what we do to make sure that they are separated is we'll do things like Megger testing, where we induce a voltage and see if there's any breakdown. That tests the insulation. So we have separation, we have insulation that keeps things separate, whether it be rubber, it could be any type of insulating materials. We do all of this to keep these two things separate, and then we'll come in and we'll confirm that that insulation is there and effective by imposing over voltages, higher voltages, to look for any breakdowns in the insulation. We want that separation. It's critical to the performance for grounded systems and ungrounded systems too. Doesn't matter. So grounding and bonding is a very important topic. We have a great resource available from IAEI. If you go to IAEI.org and if you go to the store and you find down here, Soars, Grounding and Bonding, old Eustace, he would be happy. And you have the 2023 edition. You've got we have it in a 3-volume set. Grounding and Bonding Fundamentals, Grounding and Bonding Common Applications, Grounding and Bonding Specific Applications. You can buy them individually or buy all 3 of them together. It's cheaper if you buy them together. It's only $71. That's insane. It's absolutely insane. That book should be like $100 and some, in my opinion. I've got a lot of engineering textbooks. This one is one of the best. You can buy older editions at lower prices. There's the 2020 edition. So, great resource for you, available online right now. And I would argue that we should be talking at our section meetings and division meetings, at all of our IAEI meetings, we should be doing fundamentals for grounding and bonding as part of our curriculum. Even if you do a 2-hour session and you do 15 minutes, pick a ground. You've got a ton of slides to pick from. You can pick and choose what you need for whatever program that you're working on, and do that today. All right, so get those grounding and bonding programs scheduled. Get your books on order for those programs. Get this PowerPoint slide deck. You need it. And get out there and start educating. Bring people up to speed on the fundamentals of grounding and bonding. It is critical for safety in our electrical industry. All right, that's all I had for today. Again, I hope you enjoyed the recorded session. I hope you got something out of our discussion. I hope I stirred some debate in your mind and maybe some thoughts, and I hope you've been chatting throughout the entire session. Hit that thumbs up. Don't forget to subscribe. Thank you for what you do for the electrical industry and for electrical safety. Remember to stay safe, and please, by all means, stay healthy. See you next week.